Astronomy GCSE Topic 9, Exploring the Moon. Not a very big topic, this one. I'm going to cover all of this topic in one video. We remember from some earlier topics the diameter of the moon is about 3,500 kilometers. It's about a quarter of the Earth's diameter. It's 350,000 kilometers from Earth. It's slightly egg-shaped with the fat end pointing away from the Earth. Very important, one side of the moon always faces Earth. We say that it's tidally locked. We always see one side of the moon. The moon takes 27.3 days to orbit the Earth, and we know about the formation of craters and mare. We can explain where they came from. We need to know a little bit about the internal structure of the moon. There are similarities with Earth, but then there are differences. The moon doesn't have a magnetic field, at least it has a very, very weak one. And that's because it doesn't have a large iron core like the Earth. It's got very little iron in it. Its iron core is much smaller. It does have a crust, which is about 50 kilometers thick. And it has a mantle underneath. Using radioactivity to date the rocks that we've got back from the moon, we know that it's made of very, very similar rocks to the Earth, a little bit younger apparently. Now this is the Soviet spacecraft Luna 3, and this is very important because in 1959 it orbited the moon and it took photographs of the far side of the moon, which it sent images back to Earth. So that was the first time we actually saw that humans saw what the far side of the moon looks like from this spacecraft. Since then there's been, all of the Apollo missions that went to the moon orbited the moon and had a jolly good look what's on the other side. And this is the far side of the moon. If you remember, you should remember what the near side of the moon looks like. How is it different? Can you remember any differences between it and the near side? Here's both of them together. You'll notice that the far side has lots of craters, very few maria. There's only 1% of the surface has maria compared with 32% on the near side. And the surface is older than the near side. When there's a large impact, then that creates these big puddles of molten rock which become maria. And so this hasn't happened very much on the far side of the moon. The surface is a lot older than on the near side. Why are these differences? Well, the best theory for that is that the far side cooled down slower than the near side, and so its crust is thicker. Now, why did it cool down slower? Because for many, many millions of years, the Earth was radiating a lot of heat, and a lot of that was shining onto the surface of the moon, and the side of the moon facing the Earth didn't cool down very quickly. Okay, large impacts did not penetrate the crust and so did not cause lava flows as they did on the near side, as I mentioned earlier. But as the Earth cooled down, it was radiating a lot of heat, and that kind of kept the near side warm, and so it didn't develop as thick a crust as the far side. Origins of the moon. Now, there are three theories that we should be aware of. They're the giant impact hypothesis, the Coaccretion Theory, and something called capture theory. Now, if you watch, there's an excellent ESA video on YouTube, What is the Origin of the Moon? And that actually mentions a fourth theory as well. But these are the three that we need to know about. The giant impact hypothesis, when the Earth wasn't very old, about 4.5 billion years ago, a very, very large object smashed into Earth, an object the size of Mars. It was a glancing blow. They've called it Theia. because apparently in Egyptian mythology, Thea was the goddess. No, Selene was the goddess of the moon, and Thea was her daughter. Anyway, this big object smashed into the moon, smashed into lots and lots of little bits and bits of the Earth as well, and this all formed a giant ring of debris which orbited the Earth, and then all of this stuff came together and formed the moon. And that's called the giant impact hypothesis. The co-accretion theory. Now, I've said what the word accretion means. Accretion means when you add to it bit by bit by bit by bit, and it gets bigger and bigger and bigger and bigger. If you imagine rolling a snowball downhill, then it gets bigger and bigger and bigger, and that's accretion. And when the Earth formed in the early solar system from something called an accretion disk. We'll meet these things later on when we see different types of stars. But this disk of rotating material, spinning material, and one theory is that the Earth and the moon formed at the same time from the same disk of material. That's the co-accretion theory. The third theory is called capture theory, and basically a very, very large asteroid or something came a bit too close to the Earth. It didn't crash into the Earth, but it was trapped into an orbit. Now, we know that this is how Phobos and Deimos, which are the moons of Mars, they were captured from the asteroid belt. And one theory is that that's where our moon came from. So which theory is the most likely? Well, the evidence is rocks on the moon are very similar to rocks found on Earth, and that suggests that the Earth and the moon have the same origin. The moon has very, very little iron, and that suggests that the moon could have originated from the rocks that make up the Earth's mantle and crust. In other words, the kind of the outside bit of the Earth. The moon is a bit younger than the moon, and that suggests that it formed slightly later than the Earth. And these three bits of evidence do tend to point towards the giant impact hypothesis. So scientists reckon that that is the most likely. Escape velocity. Now, what does that mean? Throw a ball up in the air, and basically what goes up must come back down again. The ball goes up and then it comes down. Why does it come back down? Because the force of gravity pulls it back downwards. The force of gravity will slow it down on the way up and then speed it up on the way down. Now, if we think about energy, what's happening is that we give the ball kinetic energy, and then as it travels upwards, it loses its kinetic energy and it gains gravitational potential energy. And how much it gains will depend on how much kinetic energy we give it. Now, as we move away from the Earth's gravity gets weaker and weaker. It follows an inverse square law. And that basically means that at twice the distance, it's a quarter as much. Or at 3 times the distance, it's a ninth. 1 over r squared. It follows an inverse square law. So at the Earth's surface, the Earth's gravity is about 10 newtons per kilogram. At twice that distance, it's about 2.5. Now, if you can get far enough away from the Earth, then you can actually escape its gravity altogether. Now, to do that, we would have to throw our ball up very, very fast. We'd have to give it lots and lots and lots of kinetic energy. How fast would we have to throw our ball up in the air? Well, that's called its escape velocity. Okay? The escape velocity of the Earth is 11 kilometers per second. That means, now ignoring air resistance, that means that if you threw your ball up in the air at 11 kilometers per second, then you'd never see it again. Okay? It would escape the Earth's gravitational field. The Saturn V rocket, which was used for Apollo, the Saturn V rocket that took people to the moon, actually reached, when it got into space, it reached a speed of 10.5 kilometers per second. It's just traveling very, very fast. Not quite 11 kilometers per second, but by the time it shut down its engines, that was enough kinetic energy. It was traveling fast enough to get to the moon. Okay, not quite the Earth's escape velocity, but enough to reach the moon. In 2007, I visited the Kennedy Space Center in Florida. I've actually been there a couple of times, but in 2007, I was very lucky. I saw a shuttle take off from the VIP seats as well, okay, which was pretty amazing. And they have something there called the Saturn V exhibition. And there's a rocket there, which was never used, and it is absolutely massive. It was the most powerful machine ever made at the time. This is before they built the Large Hadron Collider, but pretty amazing. And that's me underneath some Saturn V rocket motors.